Good morning. Today we are going to discuss the fourth colligative property of solution, osmosis and osmotic pressure. First, let's see what do you mean by the term osmosis. Osmosis is the flow of solvent through a semi-permeable membrane to solution. Now you can see on the board. This is our solvent, this beaker, and this beaker is our solution. Now osmosis is, now these two beakers are at the same pressure, that is at P atm. Now osmosis means the flow of solvent molecules, solvent to solution through a semi-permeable membrane. This is our semi-permeable membrane. Now the semi-permeable membrane is made up of, they are thin sheets which are made up of micropores. So only solvent molecules will pass through this semi-permeable membrane. It will not allow solute molecules to pass through it. So osmosis is the flow of solvent molecules through semi-permeable membrane to the solution. Now we can say that osmosis always takes place from dilute to concentrated solution. Dilute to concentrated solution, or we can say osmosis takes place from low concentration to high concentration. When I say low concentration and high concentration, low concentration means the number of solute particles are less. High concentration means number of solute particles are more. So whenever you hear the concentration term, it is based on solute particles. So low concentration means low or less number of solute particles, and high concentration means more number of solute particles. So osmosis always takes place from low concentration to higher concentration, or from dilute solution to concentrated solution. Dilute solution has less number of solute particles and concentrated solution has more number of solute particles. Now, suppose I apply a pressure greater than P atm. So I am going to apply a pressure greater than P atm, and I am going to represent that pressure with pi. We call this pressure pi as osmotic pressure. And I have applied this pi to solution site. So I have applied a pressure to solution site. We can see that the process of osmosis stops. That means there will be no flow of solvent through the semi-permeable membrane to the solution site. So what do you mean by the term osmotic pressure? And that osmotic pressure is denoted by pi. Osmotic pressure is the excess pressure that is applied on solution site to prevent osmosis. That is, to stop the flow of solvent molecule into solution. That is osmotic pressure. Now, osmotic pressure is a colligative property because it depends upon the number of solute particles and does not depend upon their nature. So we can say that osmotic pressure is a colligative property. And osmotic pressure of a solution is directly proportional to the molarity of the solution. So far in the other three colligative properties we discussed. The three colligative properties, that is not, first one is relative lowering of vapor pressure. The second and third colligative property, elevation of boiling point and depression in freezing point, those colligative properties were proportional to molality. Whereas osmotic pressure is proportional to molarity of the solution. So I am going to write pi is equal to CRT, where pi is the osmotic pressure, C is molarity, R is the gas constant, and T is the temperature. So this is the expression to find osmotic pressure. Pi is equal to CRT. Now I am going to substitute for the molarity C. We know that molarity C is equal to NB by V, number of moles of solute by volume of solution in liters. So pi is equal to NBRT by V. Next, I am going to substitute for NB. We know that NB is equal to given mass by molar mass. So, next again I am going to substitute for pi. Pi is equal to WBRT by MB into V. From this, MB is equal to NB is equal to WBRT divided by pi into V. So, this is the expression to find the molecular mass of a solute from osmotic pressure. WB is the mass of solute, R is the gas constant, T is the temperature, pi is our osmotic pressure, and V is the volume of solution in liters. So, this is the expression MB is equal to WBRT by pi V. Now, next, this osmotic pressure has more advantages than other colligative properties. Now, there are three advantages for osmotic pressure over other colligative properties. The first advantage is that the pressure measurement is around room temperature. Now, the second advantage is molarity of the solution is considered instead of molality. And the third is this, even for dilute solutions, the magnitude of osmotic pressure value is very high, which means this osmotic pressure can be used to find the molecular mass of even larger molecules such as biomolecules like proteins and also polymers. So, these are the three advantages of osmotic pressure over other colligative properties. The first one is the pressure measurement is around the room temperature. Second, molarity is used instead of molality. Now, third is even for dilute solution, the magnitude of osmotic pressure value is very high. And this molecular mass can be calculated with the help of this osmotic pressure value even for large molecular mass molecules like proteins and polymers. Now, next we are going to see a term called reverse osmosis. Reverse osmosis. Now, in reverse osmosis, the direction of osmosis can be reversed. That means usually the osmosis means flow of solvent from solvent to solution. Now here the flow of solvent will be from solution to solvent. So here how can I reverse the process of osmosis? By applying a pressure greater than osmotic pressure on solution site. Okay, so apply pressure greater than osmotic pressure on solution site. In that case, the solvent molecules will flow from solution to pure solvent. Now, this reverse osmosis is used in the desalination of seawater. That means, suppose we have two containers separated by a semi-permeable membrane, and this container, suppose this container contains our seawater. Now, I am applying a pressure greater than osmotic pressure pi to this solution site. Now we can see from the solution solvent will pass to this beaker and we get here pure solvent, means pure water. So that is called desalination of seawater, and usually the semi-permeable used here will be made up of cellulose acetate. That is the semi-permeable usually used here for desalination of seawater. Cellulose acetate will allow only pure water, that is solvent, to pass through it, whereas the impurities will be left out in this beaker. So this is reverse osmosis. Reverse osmosis means if a pressure greater than osmotic pressure is applied on solution side, then the solvent will flow from solution to the pure solvent through a semi-permeable membrane. Next, we are going to discuss three types of solutions based on osmotic pressure. They are, first is isotonic solution, second is hypertonic solution, and third is hypotonic solutions. Now, isotonic solution means two solutions with same osmotic pressure. They are isotonic. Two solutions having same osmotic pressure. Now, hypertonic solution means solution having high osmotic pressure. High osmotic pressure means the amount of or the number of solute particles will be greater, or you can say this is a highly concentrated solution. Isotonic solution means the solute concentration will be high. High osmotic pressure means high solute concentration. And the third is hypotonic, which has low osmotic pressure, means the solute concentration will be low. Low solute concentration. So we know that always the osmosis takes place from dilute to concentrated solution or low concentration to high concentration. So here we know that high osmosis takes place from hypotonic to hypertonic solution. Hypotonic to hypertonic. Now, if the solution is hypertonic, suppose we add a substance to hypertonic solution. Hypertonic means more concentration of solute particle. Suppose I add a substance to it. In that case, the solvent or water will come out of the substance to the hypertonic solution, which means that substance will shrink. So if the solution is hypertonic, and when we add some substance to that hypertonic solution, that substance will shrink. So hypertonic solution, the substance will shrink. Now suppose we add a substance to hypotonic solution. So hypotonic solution has less concentration of solute particles. So what happens? The water will flow from hypotonic solution to the substance and the substance will swell. So if the solution is hypotonic, the substance will swell. Okay, for example, you put raisin in sugar syrup. Sugar syrup, you know, it contains a high concentration of sugar particles. So that's a hypertonic solution. So in this case, the water from raisin will go into the sugar syrup and the raisin will shrink. Whereas you put the raisin, dry raisin in water. The water has low solute concentration, so water will go into the raisin and you know the raisin will swell. So that is a hypotonic solution, whereas the first one, raisin in sugar syrup, is a hypertonic solution. So this is the three types of solutions based on osmotic pressure: isotonic, hypertonic and hypotonic. Isotonic means solutions, two solutions with same osmotic pressure. Hypertonic is a solution with high osmotic pressure, and hypotonic is a solution with small or low osmotic pressure. If the solution is hypertonic, the substance added to it will shrink. If a solution is hypotonic, substance added to it will swell. Okay, so with this we complete our osmosis and osmotic pressure. Now last we have a term called abnormal molar mass. Abnormal molar mass. Now, we know that the relation between colligative property and molecular mass. Now we know that from all the 4 colligative properties we got an expression to find the molecular mass of solute. Now if I write the expression for molecular mass of solute from elevation in boiling point, the expression is Mb is equal to 1000 kb Wb divided by delta Tb into Wa. You can see this is our colligative property, that is elevation of boiling point delta Tb. This is our molar mass. They are inversely proportional to each other. Means as colligative property increases, the molecular mass decreases. Colligative property decreases, molecular mass increases. So usually, and we know these colligative properties are observed when we add a non-volatile solute. Now when you add this non-volatile solute, suppose the solute added is a non-electrolyte. Non-electrolyte. Now what do you mean by electrolytes? Electrolytes means they are substances when added to water will undergo dissociation. They dissociate into ions. Non-electrolyte means there will not be any dissociation into ions. Suppose the non-volatile solute added is a non-electrolyte. In that case, you will get the actual value of molecular mass for the solute. That means we have a normal value for molecular mass that we calculate. Okay, so when you add that non-volatile solute, the molecular mass value obtained after calculation will also be the same if the non-volatile solute is a non-electrolyte. But if we add an electrolyte, but most of the non-volatile solute added will be an electrolyte. So if when we add a non-volatile solute to a solvent which is an electrolyte, in that case that solute can undergo either dissociation or association. So if the electrolyte added or solute, non-volatile solute added is an electrolyte, it undergoes either dissociation or association. That solute can undergo either dissociation or association. Now in this case, the value of molecular mass obtained will not be the same as the normal molecular mass, and we call this value as observed molecular mass. That is the molecular mass value that we get from the colligative property, that we call it as observed molecular mass. The other one, that is the actual molecular mass that we calculate, that is our normal molecular mass or calculated molecular mass. Okay, so we can give a definition for abnormal molecular mass. This is the definition. When the molecular mass of a substance determined by any of the colligative property comes out to be different from its normal value, it is called abnormal molar mass. And an abnormal molar mass is observed if the solute undergo dissociation or association. Now I am going to give an example for dissociation and association of solute. Suppose I add sodium chloride to the solvent. Now you know sodium chloride is a electrolyte, good electrolyte. So immediately dissociate into Na plus and Cl minus ions. So when I add the sodium chloride to solvent, the number of ions increases because it undergoes dissociation. Number of ions increases. Then when number of ions increases, you know the number of particles in solution increases. So colligative property increases and molecular mass of that solution or of that solvent decreases because molecular mass and colligative properties are inversely proportional. So sodium chloride when added, it dissociates into ions, number of ions, or we can say sodium chloride is our solute. So number of solute particles increases because colligative properties depends upon the number of solute particles. When solute particles increases, colligative properties increases and molecular mass decreases. Now, suppose I am adding acetic acid to benzene. So, this is the example for association. Acetic acid to benzene. So, our solvent is benzene and we are adding the solute acetic acid. Now, acetic acid, it will dimerize in benzene. Dimerize. Dimerize means it will exist as two molecules together, and the dimer formation is through hydrogen bonding in acetic acid. So, I'll show that dimer formation of acetic acid. CH3COOH. This is one acetic acid molecule. Now, the second acetic acid molecule is CH3COOH. Now, the hydrogen bond is between this and this. OH of one acetic acid and CO of the other. CO of the one acetic acid and OH of the other. So, this is our dimer. Acetic acid existing as dimer in benzene. So, here you can see, in this case we have association. Now, when there is association, what happens in solution? The number of particles decreases. When number of particles decreases, colligative property decreases, molecular mass increases. Okay, so this is what happens when you add a non-volatile solute. It undergoes either dissociation or association. If there is dissociation, then the molecular mass, the observed molecular mass, that is the molecular mass that we get from colligative property value, will be greater than the normal molecular mass. And if there is association, then the observed molecular mass will be lower than the normal molecular mass. Okay. Now, next, Vanhof factor I. So, this is abnormal molecular mass. Next, we are going to discuss Vanhof factor, denoted by small I. Now, Vanhof, he introduced, to make these corrections for abnormal molecular mass, he introduced a factor I, known as Vanhof factor, and to account for this extent of association or dissociation. And this is the definition for I. Vanhof factor is defined as the ratio of observed colligative property and normal value. That is, if you write the expression I is equal to observed colligative property, observed colligative property by normal colligative property. Okay. So, Vanhof factor I is equal to observed colligative property by normal colligative property. Now, or the definition is, it is the ratio of observed colligative property to normal colligative property. Now, if you write this in terms of molecular mass, I is equal to, you know, colligative property and molecular mass are inversely proportional. So, I is equal to normal molecular mass divided by observed molecular mass. Now, there is another expression to find I, the value of I is equal to total number of particles, after association or dissociation divided by number of particles before association or dissociation. So, these are the three different expressions to find the Vanhof factor I. Now, for the last one, that is number of particles after dissociation or association by particles before association or dissociation. I will give an example. You take sodium chloride. Sodium chloride will dissociate into Na plus Cl minus. So, the total I value, I is equal to total number of particles after association, that is 1 plus 1. If you look at the stoichiometric coefficient, 1 plus 1, 2 by, here we have only 1, 2 by 1, so it is equal to 2. So the I value for sodium chloride is equal to 2. Okay, now even for potassium chloride, I value is 2. Then for magnesium sulfate, I value is 2. Now for potassium sulfate, what will be the value of I? K2SO4 will dissociate into 2K plus SO4 2 minus. So I will be equal to 2 plus 1 3 divided by 1, which is equal to 3. So that is the Vanhof factor I for K2SO4. Now look at acetic acid. Acetic acid will undergo association. So association means we have CH3COOH. COOH plus CH3COOH will undergo association to form CH3COOH twice. So here I value will be number of particles after association, that is 1. Look at the stoichiometric coefficient here, it is 1. So 1 divided by number of particles before association is 2. 1 and 1 plus 1 2. So it is equal to half or 0.5 I value. So this is how we calculate the I value. Okay. Now next we can predict whether, by looking at the I value, we can predict whether the solute undergoes association, dissociation, or will it not undergo association or dissociation, means it behaves as normal electrolyte. For that, if I is equal to 1, the solute behave as normal electrolyte, means no association or dissociation. Nothing has happened, no association or dissociation. Now, if I is greater than 1, in that case, the solute has undergone dissociation. And if I is less than 1, the solute has undergone association. So by looking at I value, you can predict whether the solute has undergone association or dissociation. I greater than 1 is dissociation, I less than 1 is association. Now next we can write, so when you calculate depending on the solute added, when we find the expression for molecular mass of solute, you can add this Vanhof factor also along with the expression of molecular mass. So we can write the modified form of expressions for the molecular mass of solute for all the 4 colligative properties. The first colligative property was relative lowering of vapor pressure. So the modified form, that is including Vanhof factor, is P naught A minus PA divided by P naught A will be equal to I into XB. Now the second is delta TB is equal to I into KB into small m. Now the third one is delta TF equal to I into KF into small m, and the last one is osmotic pressure, that is pi V is equal to I CRT. So these are the modified expressions of molecular mass of solute when the solute undergoes dissociation or association. Okay, so with this the chapter is over. Thank you.